Okay, in this lecture, we're going to start our section 3.4 material on the case of repeated roots of the characteristic equation and a method called reduction of order. So let's start by considering the same sort of problem we've been working with so far throughout chapter 3. That is, let us consider a homogeneous linear equation that has constant coefficients. So something like ay double prime plus by prime plus cy equals 0. And we've already seen that to solve this type of differential equation, we're going to consider solutions of the form y equals e to the rt power, where r has to satisfy the characteristic equation ar squared plus br plus c equals 0. Which is this quadratic characteristic equation. And in our earlier sections, we've already considered the case where the roots of that quadratic are real and distinct, two different real numbers, or where we had complex conjugate roots of that characteristic equation. But what about the case of repeated roots? So what if this characteristic equation has repeated real roots, let's say r1 and r2, which are the same real number? So if we take that r1 and r2 value and substitute into the form that we were considering, e to the rt, we get e to the r1 times t as one of our solutions. And then a second solution we will show is given by t times that same exponential. And our general solution in this case is given by c1 times e to the r1t plus c2 times t e to the r1t. These two solutions form a fundamental set, so our general solution is then a linear combination of those two. And we're going to justify that those two solutions form a fundamental set a bit later in this section. But for now that we know how to construct the general solution in the case of a real repeated root, let's look at some example problems. So in this first one, we are asked to find the general solution of each differential equation and then describe the behavior of our solutions as t approaches infinity. So in part A here, we have 9y double prime plus 6y prime plus y is 0. It is a second order linear homogeneous equation with constant coefficients. And so I know to solve this, I would seek solutions of exponential form. Something of the form y equals e to the rt. So that r would have to be a root of the characteristic equation 9r squared plus 6r plus 1 equals 0. And this quadratic can be factored as 3r plus 1 quantity squared is equal to 0. So we have here a single root of negative 1/3, but there were two factors of r cubed plus 1 that could equal to 0. So we have a root of multiplicity 2 here, a double root. And in this case that we have a real repeated root, a real number of multiplicity 2, we know that our general solution, y of t, is given by c1 times e to the rt, so the negative 1/3 t power, plus c2 times t, e to the negative 1/3 t power. Or if we want, we could factor out a common exponential here. And we have y of t would be e to the negative t over 3 times c1 plus c2 times t. So we have our general solution, or in the factored form. And then we're asked, how do the solutions behave as t approaches infinity? So here we see that our two roots, really a single repeated root, r was negative 1/3. So we have this exponential decay term for both factors. And so as t approaches infinity, our solution, y of t, will approach 0, because both of the roots here were negative. So our two terms exhibit exponential decay approaching 0. And then looking at part B of this example, we have the same sort of equation, 16y double prime minus 24y prime plus 9y is 0. So again, we would look for solutions of exponential form, y equals e to the rt. And so r then has to be a root of the characteristic equation, 16r squared minus 24r plus 9 equals 0. And this factors as 4r minus 3 quantity squared is equal to 0. So we have a single real root of multiplicity 2, or a double root, 3/4 and 3/4. So in this case of a repeated real root, our general solution is given by y of t equals c1 times e raised to the 3/4 t power plus c2 times t, e raised to the 3/4 t power. Or again, if you want, you could factor out the common exponential term, e to the 3/4 t power. We're left with c1 plus c2 times t. So either expression that you prefer there would be our general solution. And again, we're asking what happens to our general solution as t approaches infinity. So let's look at it. As t approaches infinity, our general solution, y of t, exhibits exponential growth. We have our two roots, or one repeated root, is a positive 3/4. So both of these exponential terms exhibit exponential growth, or if we factor out the common exponential, we have exponential growth times some linear term. So the values of y of t here will approach either positive or negative infinity, depending on the value of these constants, c1 and c2. So here we could approach positive and or negative infinity, depending on the constants, what sign they have. Okay. So here we would expect that our solutions will either approach 0 if our repeated root is a negative, or our solutions will increase without bound in either the positive or negative direction, depending on the sign of our constants, if the roots are positive. So let's look at some other examples illustrating this case of repeated real roots with initial conditions given. So in this next example, we are asked to solve the initial value problem, y double prime minus 6y prime plus 9y equals 0, with initial conditions y of 0 and y prime of 0 are 0 and 2. And then plot the graph of this solution and describe how it behaves as t increases. So when we look at this equation, we see that it is a second-order linear homogeneous equation with constant coefficients. And for these types of problems, we seek solutions of exponential form, which means that this constant r would have to satisfy the characteristic equation 1r squared minus 6r plus 9 is equal to 0, which can be factored as r minus 3 quantity squared is equal to 0. And so we have a real repeated root of positive 3. So here, since I see both of my roots are positive, right away I know that my solution will either approach positive or negative infinity. To determine which one, we need to finish our problem. So here I've got the case of a repeated real root, r equals 3. So my general solution, y of t, is given by c1 e to the 3t plus c2 times t e to the 3t. And from here, I want to solve for c1 and c2 by applying my initial conditions. And as we've seen in the earlier sections, to apply the second initial condition, we need to find our derivative, y prime, for this general solution. So differentiating the first term using the chain rule, we have 3c1 e to the 3t, plus for the second term, we have our constant c2, and using the product and chain rules, we would have a derivative of 3t e to the 3t power plus 1 times e to the 3t power. So now applying our initial conditions, y of 0 gives us c1 times e to the 0, so just c1, plus c2 times 0. So we just have c1, and we were told that this must be equal to 0. And applying our second initial condition, y prime of 0, we have 3c1 plus c2, which has to equal 2. And since c1 was 0, well, that just means c2 is equal to 2. So our general solution, or our solution of this initial value problem, y of t, is given by c1, which was 0, plus c2, which was 2, times t e to the 3t power. So this would be our solution of this initial value problem. And as t increases towards infinity, we can see that clearly our solution y of t would approach positive infinity. Both 2t and e to the 3t would increase without bound, so the product also increases towards infinity. And in the notes, I've given a plot of our solution. At time 0, our y value is 0, so we satisfy our initial condition. And the slope of the tangent line to the curve here is given by y prime of 0, which is 2. And we see that over a short time interval, as t increases from 0 to 1, our solution rapidly begins to increase towards positive infinity. So let's consider another one. Same sort of question. We are asked to solve the initial value problem, y double prime plus 4y prime plus 4y equals 0, with initial conditions y of 1 is equal to 1 and y prime of 1 is equal to 1. So notice here our initial conditions are a little bit different from what we've been considering. Normally we have y and y prime at time 0. Here we have these conditions at time t equals 1. So we want to solve this initial value problem and then plot the graph of our solution and describe its behavior as t increases. So same sort of approach to this problem. We start by looking for solutions of the form y equals e to the rt power, which means that r is a root of the characteristic equation r squared plus 4r plus 4 is 0, which can be factored as r plus 2 quantity squared equals 0. So we find that we have a repeated root of negative 2. And at this step, once I see that my roots are negative, I know that my solution is going to approach 0 as t becomes large. So right away I know my limiting behavior without even having to finish out the problem. But let's go ahead and find our solution and verify that we have a 0 limit. So in this case of repeated real roots, our general solution, y of t, would have the form c1 times e to the negative 2t plus c2 times t e to the negative 2t. And to apply my initial conditions, I also need to find my first derivative, y prime of t. So differentiating the first term by the chain rule, I have negative 2c1 e to the negative 2t plus c2, and applying the product and chain rule, I would have 1 e to the negative 2t minus 2t e to the negative 2t. And from here, I'm ready to apply my initial conditions. Now let's keep in mind that we're given the initial values of y and y prime not at time t equals 0, but at time t equals 1. So let's see what we have here. If we substitute 1 into our general solution, we have c1 e to the negative 2 plus c2 times 1 e to the negative 2. I was told that value has to be 1. In substituting 1 into the derivative of our general solution, we have negative 2c1 e to the negative 2 plus c2 times 1 minus 2, so times a negative 1, gives us negative c2 e to the negative 2, which also has to equal 1. So there's a number of ways I could go about solving here. One thing that I think I would do first is multiply both sides of this equation by e squared in order to simplify these equations a bit. So if I multiply both of these equations on both sides by e squared, I have my first equation would be c1 plus c2 equals e squared. And my second equation would be negative 2c1 minus c2 equals e squared. And if I now add these two equations, I see that my c2 term cancels, and I have negative c1 equals 2e squared. So c1 would be negative 2e squared. And then to solve for c2, I could use one of my earlier equations. So from the first equation, we know c2 is equal to e squared minus c1. And since c1 is negative 2e squared, we end up with a total of 3e squared. So now substituting these constants back into my general solution, I find that y of t would be given by c1, which is negative 2e squared, times e to the negative 2t, plus c2, which is 3e squared, times t e to the negative 2t. And I can simplify this expression a bit by combining some exponential terms. So here, where I have e squared times e to the negative 2t, I can combine those exponentials by adding the exponents. So I have negative 2 times e raised to the 2 minus 2t power. And doing the same thing for my second term, I can group my e squared and e to the negative 2t, leaving me with 3t e to the 2 minus 2t power. Or if we prefer, we could factor out that common exponential, e to the 2 minus 2t power, and we're left with negative 2 plus 3t. Now, as t approaches infinity, our solution y of t, as we would expect, approaches 0 because we have exponential decay occurring out in front of this linear term. E to the 2 minus 2t power approaches 0 the larger that t becomes. And we can verify this by plotting our solution. At time t equals 1, where our initial value is given, the value of y is 1, and the slope of the tangent line to our solution, y prime of 1, appears to be 1. And then as we follow our solution, as t increases, we see that our solution looks to decay towards y equals 0.